Ready to dive into some seriously big questions today? We're talking about the kind of mysteries that make you stare up at the night sky and wonder. And we've got the perfect guide for this journey.
It's always exciting to explore these cosmic puzzles.
It really is. And joining us is physicist and innovator Raymond Caldas to help us unpack some seriously mind-bending stuff. He's been on the front lines of research, exploring new mathematical frameworks that could rewrite our understanding of the universe.
His work is groundbreaking, tackling those questions that have stumped physicists for decades.
Absolutely. And, we like to go deep on this show, so buckle up. We've made incredible discoveries in space, mapping galaxies, understanding how stars are born and die. But some things just don't quite add up with our old ways of thinking about physics and math.
It's like trying to understand a symphony with just a few musical notes. We need a richer language, a new set of mathematical tools to grasp the complexity of the universe.
And speaking of complex, let's talk about dark matter and dark energy. The ultimate cosmic mystery, right? We can't see it, we don't fully get it, but it supposedly makes up the vast majority of the universe. It's like the ultimate cosmic game of hide and seek, and the universe is winning.
It's a fascinating puzzle. We know dark matter and dark energy exist through their effects, their gravitational influence on the things we can see.
So how do we know if we can't see them?
Well, think of it this way. Imagine watching a galaxy spinning. Now, based on the visible matter, the stars and gas we see, that galaxy should be flying apart. It's spinning too fast for gravity to hold it together.
So something invisible must be providing extra gravity.
Exactly. It's like an invisible scaffolding holding those galaxies together, and that's dark matter at play. And then we have dark energy, an even more mysterious force that seems to be pushing everything in the universe apart at an accelerating rate.
Wait, so instead of slowing down, the expansion of the universe is actually speeding up, like someone hit the gas pedal.
Precisely. It's one of the most perplexing discoveries in modern cosmology, and it completely changes our understanding of the universe's fate.
Okay, this is already blowing my mind, and we're just getting started. So we've got this invisible matter holding galaxies together, and an unknown force pushing everything apart. Where do we even begin to look for answers?
That's where these new mathematical approaches come in, offering a fresh perspective on these cosmic mysteries.
Okay, I'm ready to dive into those new approaches, but before we do, we have to talk about black holes. I mean, even the name sounds like something straight out of science fiction.
They're certainly among the most extreme and mind-boggling objects in the universe. Places where gravity is so intense that nothing, not even light, can escape their grasp.
So how does something even become a black hole?
Imagine a star, much more massive than our sun, reaching the end of its life. It collapses under its own gravity, squeezing all its mass into an incredibly tiny space.
And that's when things get really weird.
You could say that. At the center of a black hole, you have something called a singularity. It's a point of infinite density where our current laws of physics simply break down.
Okay, so we've got dark matter, dark energy, black holes. It's like the universe is throwing one giant cosmic curveball after another. I'm starting to see why we need new math, new ways of thinking to even begin to wrap our heads around these concepts.
Absolutely. It's like we need a new set of lenses to see these cosmic phenomena clearly.
So where do we even begin to find the math that can explain something as dense as a black hole singularity?
Well, that's the exciting part. There are these brilliant minds out there developing entirely new mathematical frameworks. One area that's particularly fascinating is non-commutative geometry.
Okay, I'll admit that sounds a little intimidating. What's so different about non-commutative geometry?
It challenges a fundamental assumption we often make about the world. Like 2 + 2 = 4, regardless of whether you do the calculation on a Monday or Friday, that sort of thing. But at the quantum level, the order of operations can actually change the result of an experiment. It's like, imagine if when baking a cake, adding the flour before the eggs gave you a completely different result than adding the eggs first. Non-commutative geometry attempts to build a mathematical framework where this kind of thing makes sense.
Wow, that's a whole new way of thinking about math. So how does this non-commutative geometry relate back to the cosmic mysteries we're trying to solve, like dark matter?
Well, one of the leading theories about dark matter involves particles that interact very weakly with each other. And these interactions, at the quantum level, might be subject to the principles of non-commutative geometry. By applying this new math, we might be able to predict how these particles behave and how they affect the universe on a larger scale.
It's like this new math gives us a new lens to study these invisible particles that make up most of the universe. Fascinating. Are there any other mathematical approaches that are changing the game?
Absolutely. Another area that's showing a lot of promise is category theory. Now, instead of focusing on the objects themselves, category theory looks at the relationships and transformations between objects.
Okay, can you give me an example of what you mean?
Sure. Think about a map. A traditional map focuses on the locations of cities, right? But with category theory, we'd be more interested in the roads connecting those cities, the distance between them, the relationships between those locations.
I see. So it's about understanding the connections rather than just the individual elements.
Exactly. And this is particularly helpful when we're trying to understand something as complex as quantum entanglement.
Right, where two particles, even separated by vast distances, are somehow linked and can affect each other instantaneously. It always felt a bit like magic to me.
Definitely one of the stranger aspects of quantum mechanics. But category theory provides a framework for describing these relationships and transformations, even when they seem to defy our classical intuitions.
So by shifting our focus to the connections, we might be able to decipher the mysteries of quantum entanglement.
Exactly. And that understanding could have huge implications. It could be the key to unlocking the true potential of quantum computing, which relies heavily on the principles of entanglement.
Okay, now we're connecting the dots to some real-world applications. Before we get there, though, I want to circle back to black holes. Does this new math offer any insights into those cosmic puzzles?
It certainly does. You see, when we talk about black holes and the singularity at their center, one of the biggest challenges is that our current theories about gravity, even Einstein's theory of general relativity, break down at such extreme densities.
So how do we even begin to describe what's happening at the heart of a black hole?
That's where a theory called loop quantum gravity comes in. This approach suggests that space-time itself isn't smooth and continuous, but is woven together from tiny interconnected loops, kind of like a chainmail fabric.
So instead of thinking of space and time as this smooth backdrop, it's more like this intricate tapestry of interwoven threads.
Exactly. And this has profound implications for our understanding of black holes.
This is all so incredibly mind-blowing. But I have to ask, how does this new math, this new understanding of the universe actually impact us here on Earth? It all seems very abstract and theoretical.
That's a great question. While these are still early days in terms of applying these new mathematical frameworks, the potential impact is huge. And one of the most exciting areas where this is playing out is in the field of quantum computing.
Okay, quantum computing. It feels like we're on the verge of a technological revolution. Everyone's talking about it, but I'll be honest, I still don't fully grasp what it is or what it can do.
It's all about harnessing the bizarre but incredible laws of quantum mechanics to perform computations in ways that were unimaginable with classical computers.
All right, so walk me through it. What makes quantum computing so different, so powerful?
It all starts with the fundamental building block of information, the bit. In classical computing, a bit can be either a 0 or a 1. But in the quantum world, things get a little weirder. Remember our conversation about quantum superposition?
Yeah, the idea that a particle can be in multiple states at the same time, like that coin landing on heads and tails simultaneously.
Exactly. Well, in quantum computing, the basic unit of information is a qubit. And thanks to superposition, a qubit can be both 0 and 1 at the same time.
So it's like having a switch that can be both on and off at the same time. That seems incredibly powerful.
It is. This fundamentally different way of representing and manipulating information is what gives quantum computers their edge. Instead of being limited to just two states, a qubit can explore a vast spectrum of possibilities simultaneously, and this allows them to tackle certain types of problems exponentially faster than classical computers.
This is really blowing my mind here, but can you give me a concrete example? What kind of problems are we talking about?
Take drug discovery, for instance. To design new drugs, scientists need to understand how molecules interact at the atomic level. These interactions are governed by the laws of quantum mechanics, which are notoriously complex and difficult to simulate on classical computers.
So we're talking about incredibly complex calculations that would take traditional computers years, if not centuries, to solve.
Exactly. But a quantum computer, leveraging the principles of superposition and entanglement, could potentially perform these simulations in a fraction of the time. This could revolutionize drug development, leading to new treatments for diseases that are currently incurable.
It's amazing to think something like drug discovery, something so important, could be impacted by something like quantum mechanics.
It really speaks to how interconnected science is, Like what seems theoretical can have these real-world impacts.
Absolutely. And on that note, we've talked about the potential of quantum computing, but I kind of want to dive a bit deeper into how it actually works. Like, at the nuts and bolts level, what are the differences between a classical computer and a quantum computer?
Well, at the heart of it is the bit, right? Like in a classical computer, the bit is the fundamental unit of information. A bit is either a 0 or a 1, like a light switch being on or off.
Right.
Quantum computing introduces the qubit. And because of superposition, a qubit can be in both states at the same time. So it'd be like that light switch being both on and off at the same time.
Okay, yeah, that's a tough one to wrap my head around.
It is.
Yeah.
It is. And that's just the start. Quantum computers can also use another one of those weird quantum things we talked about, entanglement. This is where two qubits are linked, no matter how far apart they are, and like whatever happens to one happens to the other.
Like those entangled particles, measuring one instantly affects the other, even if they're like light years apart.
Exactly. And this connection between qubits, it lets quantum computers do computations in a completely different way than classical computers.
So instead of processing stuff one bit at a time, a quantum computer can look at multiple possibilities all at once.
Yeah. Like having tons of computers working on the same problem at the same time. And this is where you get these massive speed ups for some problems.
So we talked about drug discovery, but where else could we see this quantum speed up have a big impact?
Oh, tons of places. One area that has scientists really excited is material science. Like, imagine designing materials at the atomic level, making them have the exact properties you want.
So we could have materials that are lighter but stronger, or superconductors that work at room temperature?
Yeah. Quantum computers could help us understand and change matter. Like, fundamentally. That could change everything from energy to electronics.
That's incredible. What about AI? Everyone's talking about how quantum computing will revolutionize AI.
It's definitely one of the big ones. Machine learning, which is a huge part of AI, uses tons of data and computing power. Quantum computers could make those algorithms way faster and lead to AI that's way more advanced than what we have now.
It's exciting and a bit scary to think about what that could mean. What about cryptography? I've heard quantum computers could break all the ways we keep our data safe now.
That is a concern. A lot of encryption today relies on the fact that it would take classical computers forever to factor large numbers. But quantum computers, they could break those codes really easily.
So our digital security is at risk.
It's a possibility, which is why people are working on new ways to keep data safe, like quantum-resistant encryption. It's like a tech arms race.
That is kind of scary. It seems like quantum computing has so much potential, but also a lot of challenges.
Yeah, for sure. It's powerful and could change the world, but we have to be careful and responsible with it.
This deep dive has really opened my eyes to what's possible with quantum tech. We've gone from the smallest particles to the biggest black holes, and I think it's safe to say the universe still has a lot of mysteries.
It's been fun talking about all of this with you. Trying to understand the universe is a never-ending journey.
It really is. And on that note, we'll wrap up our deep dive into the universe and the amazing new math that's changing how we see it. Until next time, keep looking up and asking those big questions. You never know what incredible discoveries might be just around the corner.